Welcome to Processor Fundamentals. This unit looks right under the hood of the computer system. We're going to strip away the software, the operating system, and the user interface to look at the actual hardware that makes computation possible. You will learn exactly how a processor fetches, decodes, and executes instructions, and why these concepts are heavily tested in your Paper 1 exam. Everything starts with the von Neumann architecture. This is the defining blueprint of modern computing, built on the stored program concept, which simply means that both data and instructions are stored in the same main memory. You will see how the processor communicates with this memory using three specific system buses: the address bus, the data bus, and the control bus. We will also calculate how the physical width of these buses directly limits your system memory and performance. Next, we zoom inside the processor itself. You will meet the control unit, the silent conductor that generates timing signals to coordinate all operations. Then there's the arithmetic logic unit, where the actual mathematical calculations and logical bit shifts happen. Crucially, you will need to master registers. These are tiny, ultra-fast memory locations built directly into the processor, like the program counter and the accumulator, each with a highly specific job that you must be able to define. All these components work together in the fetch-execute cycle. This is the continuous heartbeat of the processor. First, the program counter sends an address to the memory address register. The instruction is fetched from main memory into the memory data register and finally moves to the current instruction register to be decoded and executed. In the exam, you will need to trace this exact sequence flawlessly, predicting the contents of any register at any given moment. But how do we actually tell the processor what to do? Processors only understand machine code, which is pure binary. Because binary is incredibly hard for humans to read and write without making errors, we use assembly language. You will learn how assembly uses simple text mnemonics to represent machine code instructions, and how a piece of software called an assembler translates your symbolic labels into the raw ones and zeros the hardware demands. Finally, we explore how those instructions actually interact with memory. You will compare immediate, direct, indirect, and indexed addressing modes, learning exactly when and why to use each one to overcome memory limitations. We will also weigh up the fundamental design choices behind the processor itself. You will compare complex instruction set computers against reduced instruction set computers, evaluating how these choices impact execution speed, compiler design, and the physical hardware. This unit builds the absolute foundation for all your low-level computer science knowledge. Take your time with the definitions, practice tracing the register transfers, and remember that understanding how a computer truly works is what separates a coder from a computer scientist. You are ready to begin.